All right, we'll pick up with capillary function for this video. We've already talked a little bit about capillary structure. I even talked a little bit about blood volume in the capillaries and a few things like that, but we'll keep bringing those points in as we go. This illustration is just discussing capillary permeability. So continuous capillary is the least permeable. We still have fluid loss through there, and we'll discuss today how to quantify that to understand how much fluid is being lost. To the more leaky, the fenestrated capillary, remember we found those in the pituitary to allow little peptide hormones across to the sinusoids, which are the leakiest. We can get proteins across the membrane in those sinusoids, and I pointed out those are found in the liver because the liver is making 90+% of your plasma proteins. I even mentioned this idea of blood flow through the capillaries is mediated by metabolism, but I want to elaborate on that just a little bit here with the idea that, well, of course, the blood is going to follow the area of least resistance, right? And resistance is related to the radius to the fourth power, proportional to, I should say. Well, if you want to adjust blood flow, all you have to do is increase tension on the smooth muscle here, usually in these little precapillary sphincters that we've talked about before, and that will adjust flow through that area, right? If this radius gets smaller, the resistance goes up. And so flow would be shunted to another area. So this is one way that we can regulate flow through a capillary system, but what controls the tension on that smooth muscle? Well, metabolism is one of the major things that affects the tension on that smooth muscle. One thing is hydrogen ions, CO2. Think about some cells in here that are highly metabolically active. Well, they're going to be releasing CO2, right? And most metabolic processes also produce a hydrogen ion, so acidity. Well, those things will actually cause the smooth muscle to relax. That precapillary, relax that precapillary sphincter. So if we relax this, the radius increases, we reduce the resistance, and we get flow to the area where there's high metabolic need. So this is a form of autoregulation, and I believe I've mentioned that before, but that is one of the major ways that we'll regulate flow through these individual branches of this capillary system. Now, some of these pathways are not regulated, right? This thing called a met arteriole, that's open all the time, so we'll have some flow through that capillary all the time. But all these individual branches, and again, this is an oversimplification, there are lots more branches here, that's going to be regulated largely by metabolism. Now, when we discuss things like increasing vascular resistance, that's primarily regulated up here at this arteriole. So we can constrict these vessels, increase the resistance to flow into the capillary system itself. If this occurs over a lot of arterioles, will increase vascular resistance for the cardiovascular system. And we'll come back to that when we get to regulation. The other thing I want to really drive home here is this is the interface between the arterial and the venous system too. So this is where we transition from arterial to venous. So now we're sending blood back to the heart, so that would be part of the venous system there. But again, all of our gas exchange, nutrient exchange is going to take place here at the capillaries. And the flow running through the system is going to, so I'll just say this, flow is going to match metabolism. And that's going to be mediated by autoregulation here at the capillary level. Largely through the mechanism I just described there. There are a few other things going on, but that's the most important part. And if you understand that, I think we're actually doing fairly well with this. So, we discussed this, so we're delivering oxygen, removing CO2, hydrogen ions, other waste. We have to deliver glucose. The way we get that to happen at the level of the capillary is just diffusion. So, as I mentioned before, the capillaries are the only place this can happen because it's the only place where the walls are thin enough to allow diffusion to take place. We can't get diffusion across this wall. It's just too thick. So down at the capillaries is where we're going to get diffusion taking place. And this just follows this simple Fick equation for diffusion. So this is a simplified diagram here showing some cells right next to a capillary here. And we're showing diffusion in a couple of different directions, right? Diffusion of substances into the tissues with a couple of different areas here. It looks like they have O2. It's a little small here, but this would be like O2. Waste products diffusing back in, and these are going to be following their concentration gradients. It's as simple as that. It goes from an area of high concentration to low concentration. So that's just diffusion. So it's a little more complicated than that, as you might guess if you peeked over here at the Fick formula. Let me show you a couple of things. So I use the standard notation here of J of X. And this means this is flux of X. And I'm only including that because I know Dr. Sildorf likes to refer to this as flux. It's diffusion, right? So when we talk about flux, we're talking about diffusion across the membrane here. Granted, we can have flux of water. Technically, that would be osmosis under those circumstances, but it's still a form of diffusion. And I prefer to think of this as diffusion. So I mentioned that those walls up there are too thick for diffusion across them. So we have to understand the permeability of this vessel. In this permeability here, that's this P in the equation. So the permeability is going to ultimately determine diffusion. The surface area that you have for diffusion, that is enormous across all the capillaries. So we have huge areas for diffusion. Well, I'm talking, if I remember the stat off the top of my head, we're looking at the order of like 1,500 square meters of capillaries for diffusion. So there is massive area for diffusion. So this is really large. The concentration gradient, so concentration outside compared to inside, you can flip this either way you want, depending on where the concentration is the highest. So if it turns out, if you just plug numbers into this, for example, so if the concentration on the outside is greater than the inside, then we'll have diffusion coming in. If you get a positive number, if it's a negative number, you get diffusion out. I prefer just to put high concentration here minus low concentration, and then I just use my head and a little common sense to decide which direction this goes. Any way you want to do that is just fine. So that's our concentration gradient, and that will vary depending on the metabolism of the cells, right? And also how much of that substance is in the blood. So that's determining our concentration gradient. Now, D is diffusion distance. Now, diffusion is very efficient over very small distances. You probably, well, I don't know if they still do this demonstration or not, but in middle schools, they'll try to demonstrate diffusion by opening a bottle of perfume or something at the front of the class, and then people in the front row can smell it, and it keeps on diffusing out until other people can smell it. Well, that's a very large distance. Usually people in the back of the room are faking it by the end of that demonstration just because they want it to end. Yeah, sure, I smell it. So distance is important. We need a very short distance, so we want a short distance. And you can see that mathematically. It's in the denominator here, so the smaller that distance is, the faster our diffusion rate will be. The larger our concentration gradient, faster our diffusion rate will be. larger the area, that's a multiplier. We're multiplying that times this ratio here. So that has a very large effect on diffusion. So does the permeability of the membrane, or the capillary in this case. That has a very large effect on diffusion. And based on our capillary system, again, very short distance, right? We have cells here. If we needed to diffuse to more, we would have there'd be another capillary up here to diffuse to more cells up in this area. So the diffusion distance is kept small just by the number of capillaries that we have into the tissues. So very small diffusion distance, huge surface area because we have so many of these things. So what limits diffusion? Well, I kind of alluded to it about in the previous discussion here. It's just flow. So flow. So if you need more nutrient to a given area, we relax those precapillary sphincters and we increase the flow into that region. And that's going to determine diffusion. So we don't really have a situation usually where the rate of diffusion is really limiting delivery. We could have an example. Let's say if we had edema, and we'll talk about how that might happen. So the interstitial fluid out here, the extracellular fluid expands and starts pushing these cells away from the capillary that they're supposed to get nutrient supply from. Well, in that case, the distance increased. And if the distance is large enough, well, now the rate of diffusion is going to limit our delivery of substances to that cell if it's pushed far enough away. But normally, with normal physiology, it's really flow that's going to determine our delivery of nutrients and our removal of waste products. And it's actually that simple. Yeah, I actually don't have anything to add to that. Now, in addition to diffusion across the membranes, we do have some fluid movement as well. And that's just a form of filtration. So we also have an equation for that. It's like we have an equation for everything, right? This is known as the Starling equation. So diffusion was Fick. So that's Fick's law, second law really, I think, of diffusion. And here we have Starling for filtration. Let's take a look at some of the stuff here. It's also a form of flux, but see the V instead of the X? It's volume flux. So this is bulk flow. This is movement of fluid. I call this filtration. But it all means the same thing. So let's look at some of our factors here. This is a multiplier, this filtration coefficient that we have here. That's how leaky the capillary is to fluids. Now, if you look over here at this continuous capillary, well, it will have a certain leakiness, right? That pericellular means of fluid leakage there. But if you think about, what about those fenestrated capillaries? Ones with little holes in them. Well, they'll have a very large KF. As a matter of fact, it may be more than 200 to 400, let's say, times what we'd see in a regular capillary here. So this KF, this filtration coefficient, is dependent upon the structure of the capillary we're talking about here. So some of the capillaries in the kidney you're going to see in the subsequent sections have these fenestrated capillaries, so they'll have very large KFs. So you're going to have a large multiplier for these other factors that we haven't discussed yet that we're getting ready to talk about. So look at this, hydraulic pressure. That's just fluid pressure in the capillary. So capillary pressure, blood pressure, is what we're talking about here. And we just have a little sub C to indicate that that's pressure in a capillary. Well, there's fluid around the outside of that. So this I stands for interstitial, or you can think of that as extracellular fluid, or interstitial. Interstitial fluid around the outside of that. So this would be the fluid pressure around these cells here. So we have fluid pressure inside, that's the capillary pressure, and we also have some fluid pressure out here. And as you imagine, they would be in opposite directions, right, for filtration. If we have a lot of pressure in the capillary, we're going to be pushing fluid out. And if we have a lot of pressure out here in the interstitial fluid, it will try to push the fluid back in. So we have to understand the difference between those two fluid pressures. That's what we have here. Capillary pressure is usually higher, minus the interstitial pressure, which is usually very close to zero under normal circumstances. So this interstitial pressure tends to be very, very small. Before I get to this reflection coefficient, let's look at these other things. This is oncotic pressure or oncotic force here. Oncotic pressure, this is due to, well, really plasma proteins. So we have plasma proteins inside here, and water is attracted to protein. It's going to go toward, that's a protein. They didn't have charges on them. So the water would be attracted to that. So if we have plasma proteins in there, the water will be attracted to that. If we happen to leak some proteins out here, the water would be attracted to that. Normally, we're able to keep all those plasma proteins inside. So this is plasma, the oncotic pressure due to the plasma proteins inside the capillary, minus any protein that we have on the outside. And usually that value is zero, because we're not leaking proteins out in the interstitial fluid. Just like the interstitial pressure tends to be very low also. So let's get our major factors here. Pressure in the capillary, plasma proteins. So oncotic forces in the capillary itself. Let me make sure you understand what I'm talking about when I say oncotic. This is just osmotic pressure due to proteins. So just like water was attracted to, say, sodium, that would be an osmotic force there, or an osmotic pressure. Well, when water is attracted to a protein, we just change the name and call it oncotic pressure. It comes from the Greek meaning onkos, so it means swelling. If you have proteins out here, you'll get fluid leakage and you'll have swelling. That's really where that name came from. But it's water attracted to protein. That's just oncotic, as opposed to osmotic. And I'm going to remove that sodium because that will confuse people when they come back to look at it. So I thought my lag was getting the best of me. There we go. We got rid of it. So how do we put all this together then? So how leaky is the capillary? That's our filtration coefficient. We're going to figure out the difference between our pressures here, pressure inside the capillary versus outside, so the net pressure. And then we're going to subtract those plasma protein and interstitial proteins forces too. I didn't talk about this reflection coefficient yet, so let me go ahead and tell you what that means. That actually describes whether the proteins are leaking out or not. So we call this a reflection coefficient. You can think of it also as the permeability of that capillary to those proteins. So if we have a reflection coefficient that's 1, so that would just be 1 times whatever this difference is, that means the proteins stay inside. They're completely trapped. That means they're reflected back from the membrane if they try to leak out. So that's, again, where this idea of a reflection coefficient, I think, comes from. So it's not permeable if we have a reflection coefficient of 1. We're not losing any protein. Now, if we have a reflection coefficient of 0, then that means we have plasma proteins freely moving across the membrane. You would only see that in cases like sinusoids, where the proteins can move across the membrane. We get a little bit leaking across these fenestrated capillaries too, right? Little peptides. So our reflection coefficient, let's say for a fenestrated capillary, would be somewhere between 0 and 1. So it would be less than 1. It might be some like 0.4, let's say, for a fenestrated capillary. And I'm making that number up. I don't know what the actual reflection coefficient is for a fenestrated capillary, but it's less than 1. And I know it's not freely permeable, so it's not 0. And all you have to do here is think about this in very general terms. I just simplified this to out minus in. What are the forces pushing fluid out? Well, that's primarily hydrostatic, or hydraulic, I should say. These hydraulic forces. Pressure in the capillary, there's usually no pressure in the interstitial fluid. So pressure inside the capillary, that's pushing fluid out. The oncotic forces, that's trying to pull the fluid back in, isn't it? That's plasma protein here. If we have a reflection coefficient of 1, we're not leaking any proteins out here, so the interstitial oncotic is 0. So whatever our oncotic force is for the protein inside here, that's going to try to pull the fluid back inside the capillary. So out minus in, that's really net filtration. It's our net filtration force, I should say. And of course, we would have to take into account how permeable our system is. So this is just a very simple-minded way of thinking about it. But that's really what the formula is telling you, right? Out, in. Out minus in. So again, just to understand what's going on with filtration here. And we could plug some numbers in there and calculate a net filtration force. If we need to do that, we can do it in the reviews. Trying to keep this short. But really, it's just a matter of plugging numbers into the formula and understanding where the forces are. Yeah, that's enough. I'm not going to do some practice here. I'm going to try to keep this one short for you. And the other way of thinking about this, see if we can get a little more zoom for us. Is the forces, how they change along a capillary. Right, so we're going to have our highest pressure here leading in, and that pressure is going to drop off. We know this pressure has to be higher than the pressure here because the flow is in that direction, right? It goes from there of high pressure to low pressure. So we are going to see pressure dropping off down toward the venous side of this capillary. All right, so our pressure in the capillary pushing the fluid out gets weaker as we get further away from the arterial side. And that's indicated by these big arrows here. So we have a lot of hydrostatic pressure or hydraulic pressure pushing the fluid out, and that's getting smaller and smaller as we get further and further away. Now, we also have this oncotic force here. That's trying to pull the fluid back in, and that's shown as these arrows pointing inward here. Oops, you've reversed one. I think he's actually just flipped them. So that's going to be our oncotic force trying to pull the fluid back in because we aren't reversing the pressure there. So let's think about this in terms of the plot that we have. So this is along the length of the capillary. So we have the high pressure end here, and he's shown the pressure in the capillary right here. The pressure drops with distance. He has a fairly dramatic drop going from one end to the other. Actually, that's about right. So that's the pressure drop from the one end of the capillary to the next. The arterial end, maybe I should even note that. This is closer to the arterial. Oh, he actually wrote that right down here. Arterial, and this is toward the venule over on this other end. So the pressure drops over distance. This is our plasma oncotic pressure, and we're assuming that we have a reflection coefficient of 1.